Hello. In this video, I'm hoping to demonstrate calculating the pI of an amino acid without an ionizable R group. Let's take this one step at a time. Let's talk about the pI. The pI here is also called the equivalence point. Some people call it the isoelectric point. I guess that's what the I stands for actually. Isoelectric point. And it's literally the pH of the solution at which the substance, in this case the amino acid, has a net charge of 0. And I want to make sure I say net average charge, because if I'm at the pI or at the pH where everything is averaging to 0, and I look at the molecules, I'm not saying that every molecule has a charge of 0. I'm saying that on average, the net charge is 0. Meaning, for instance, your amino acid, 80% of the amino acids could have a net 0 charge, and then 10% could have a +1, and another 10% could have a -1 charge. But on average, when you average all of those together, it's 0. That's the pI. It's literally the pH at this situation. Now, the idea that we have a R group that's not ionizable, what does that mean? Okay. Or we could say a non-ionizable R group. It means that when we look at the pKa table, you do not have a number in this column here. So for instance, asparagine does not have a pKa for the side chain, meaning that its side chain is not ionizable. Now, I want to have a little disclaimer. The side chain, or I say the R group, is not ionizable, so you won't get a charge. Between reasonable pHs. And the reasonable range is 1 to, let's say, 13. I think that's a good range. Okay, that actually takes care of 12.5. We're above 12.5 when we hit 13. Okay, so between the pH of 1 to 13, something like glycine has no ion on the R chain or R group, or something like leucine. Between these pHs, you will never have the leucine R group have an ion. Okay. I'm not going to belabor the point. You could look at your side groups here and try to predict which one's ionizable and which is not. We're going to go over how to calculate the pI for an ionizable side group, but not in this video. We're going to go very simply with an amino acid that only has 2 pKa's. Now, the 2 pKa's are these two. We're going to look at glutamic or glutamine here. We have a 2.2 and a 9.1. We have to know what that means when I say the pKa of this group is 2.2 and the pKa for this group is 9.1. What does that mean? It means that when we get above 2.2, we are basic enough, the solution is basic enough to take off this hydrogen here. And then to take off one of the hydrogens for the amine, we have to be above 9.1. What I mean by above 9.1 means we're on the basic side of 9.1. Above 2.2 means we're on the basic side of 2.2. So something like pH of 3, right? This is important to know the terminology. So when I say pH of 3, that is on the basic side of 2.2. But pH 3 is also on the acidic side of 9.1. You know that 13 is very basic, 1 is very acidic. And so we're using the pK as sort of like the crossover point. And again, at 2.2, a pH of 3 means we're on the basic side. A pH of 1 means we're on the acidic side. When you're on the acidic side of this group, you keep the H. When you're on the basic side, you're basic enough to remove the H. So in this case, the border is the border between neutral and anionic. But for this group, the border is between positive and neutral. So when we're on the acidic side of 9.1, we keep the H, and it's positive. But when we're at like 11, we're on the basic side, and we remove 1 hydrogen and become neutral. Do you see the subtlety there? The border here is between neutral and anionic. The border here is between cationic and neutral. Let us demonstrate that. Okay, 2.2 and 9.1. For glutamine, let me talk about the pKa, and then we'll start doing the problem itself. The pKa, that is a pH, or when the pH is identical to the pKa, when they're equal, that means that 50% of the molecules are neutral and 50% are charged. Now, I'm not telling you whether it's cationic or anionic because it depends on the group. In this case, 50% are neutral, 50% are anionic. When we get rid of the H. In this case, 50% are positive, 50% are neutral when we remove one of the H's. Okay, so pK is very interesting. It's literally the border between charged and uncharged. And so the trick to calculate the PI, finally, we get to look at calculate the PI. The trick is we're going to start at very acidic conditions. pH 1, very acidic. It's not unreasonably acidic. I'll show you what I mean by that in this example. The example we're going to use is glutamine. It's an amide in the R group, right here. That amide is neither acidic or basic, meaning that that group is non-ionizable. Between pH, this is the important part, between pH 1 to 13. It's neither acidic nor basic. Now, yes, if you get super basic, like way above 13, you can make this nitrogen negative. Or if you become super acidic, you can make this oxygen positive by putting an H. But within these pH values, that should never become an ion. Let's start drawing our molecule. At pH 1, your amine is going to be protonated. Your carboxyl group will also be protonated, but in this case, it means it's neutral. Do you see what protonation can mean? Different charge states for different things. Fully protonated for an amine means it's positive. Fully protonated for a carboxyl group means it's neutral. Again, between the pHs of 1 and 13. Okay, that's super important because some of you remember, you could protonate this, okay, to get it to do Fischer esterification. But that's not pH 1. That's way below pH 1. Okay. Now the pKa's, I think they were 2.2 for the carboxyl group, 9.1 for the amine. Okay, we're about to change the pH. Right now the pH is 1, but before we change the pH, let's make a note of the charge. At pH 1, we have a positive and a neutral. So that is a net positive charge. That's net plus 1. Okay? Now let's travel. Let's travel to a new pH. But let's get to a pH where things start to change. Well, our first pKa that we're going to cross over is 2.2. So let's pick a pH of what? Let's pick a pH of 4. 4 is good because it is on the basic side of 2.2, but it's still on the acidic side of 9.1. Do you see? We want to go over 9.1 in the second round, okay, when we change from here to here, but not quite yet. So what happens when we go past 2.2? We become basic enough to remove this proton here. See, 2.2, 2.2. We cross over it, we get rid of this hydrogen. So I will draw the carboxyl group now like that. Are we basic enough to remove this proton? No. So that will stay the same. Look at the net charge now. The net charge cancels out. The net charge is 0. Let's put a 0 right here. And that's your net charge. So do you see how we went from +1 to 0? Now let's cross over pK of 9.1. Okay, let's choose 11. Okay, that's above 9.1, meaning we are now basic enough to remove this proton. Perfect. So let's remove that proton, and we become neutral. Okay, now it's still basic, so we're not going to add a hydrogen here. Okay, whoops. No, we're not going to add a hydrogen here, okay? Because we would have to be more acidic to add a hydrogen here. So this one stays. Nothing happens. We get even more basic when we go from 4 to 11. There's no hydrogen to remove anyway. So this one stays like that. Look at the net charge now. The net charge is neutral and negative. So this is net negative. Okay. And so here we traveled to net negative. The PI, finally. I'm looking at this right here. The PI is the average of the two pKa values that sandwich the neutral structure. So here it's neutral, right here. Okay. So what are the two pKa's we're going to average? The two pKa's we're going to average are 2.2 and 9.1. The equation is this: Pi equals 2.2 plus 9.1 divided by 2. Okay, get your calculator. Divided by 2. Whoops. 2.2 plus 9.1 divided by 2. Okay, 5.65. Is the Pi. Meaning that if we could adjust the pH to be 5.65, the average charge of the solution will be 0, or the average charge of the molecules in the solution will be 0. Now, am I saying that 100% look like this? No. The majority looks like this. Some still look like this. Some still look like that, but they would cancel each other out because they would be approximately equal parts. But the majority, yes, the majority would be this. And the average would be 0, for sure, at this Pi. Does that make sense? Look at where it is. It's like in the middle, right? It's in the middle of these two numbers. Because in the middle of these two numbers, we are acidic enough to remove this hydrogen. We're basic enough to remove this hydrogen, but we are not basic enough to remove this hydrogen. Now, what are you realizing? You're realizing the Pi, right? The Pi of amino acids that have no ionizable side group is just the average of these two numbers. So that's fairly easy. And you can look it up. Look at the Pi for glutamine. It's going to be in between these two numbers, 5.65, approximately. The hard part is this, and it's a different video. What if you have an ionizable group? Now your net charge of 0 is in between two other pKa's. So for instance, and I don't memorize this, I work it out. For instance, for aspartic acid, 3.9, is the pi the average between these two, or the average between these two? Okay. Now you'll see trends, but again, I don't memorize the trends for this type of problem because I know I'm going to forget it, or I'm going to totally reverse it or mix it up. I work it out, and I try to find between what two pKa's do I have a charge of 0, and then I average those two pKa's. Now the important thing is this, and then I'll conclude this video, and then I'll start working on the next one where we work with ionizable side groups. The thing is this. Let's take, for instance, lysine, pK of 10. Lysine is here. So that pK of 10, is that the border between lysine being positive and then neutral? Or is that the border between lysine being neutral and then negative? Yes, neutral then negative. Well, here it's already positive. This whole chart, by the way, is at pH 7. pH 7 right here. So let's think about it. At pH 7, it is acidic enough to be protonated. Or you can think of it this way. At pH 7, it is not yet basic enough to get rid of this hydrogen. So that tells me what 10 means. 10 is the pH at which we are basic enough to remove this hydrogen here to make it NH2 neutral. So that is the border between positive and neutral. So that's pretty easy. What's harder is tyrosine, OH. Look at tyrosine, the pK for its side group. Okay, so this is a longer video than I had planned. Let's continue. We have a little bit of momentum. 10.1, tyrosine. Okay, so I'm going to put here pKa equal to 10.1. Now, is that 10.1? Does that mean that is the pKa at which we start removing this hydrogen here and make it O minus? Or is this ionizable because at very acidic conditions, this is OH2 plus? And 10.1 is the pKa, or the pH at which we get rid of one of the hydrogens to become neutral. That's what we have to decide. Well, think about the alcohol. And again, when we do this game, when we start ripping off protons to figure out what the pi is, remember, we are only traveling from pH equal to 1 all the way up to pH possibly to 13. Between those pHs, okay, that can be an ion because it's ionizable. It has a number. What ion is it more likely to be, though, somewhere in between these two ranges, these two extremes? For an alcohol, it is more likely to become O minus than it is to be protonated and become OH2 plus. Or maybe another way you could think about it is it looks like this at pH equals 7. Okay. So at pH 7, it's neutral. As we get up to pH 10, what's most likely? Most likely is we're going to be basic enough to get rid of this H and make it O minus. So I'm pretty confident in concluding that this is the border between neutral and negative. Between neutral and negative. So that, maybe that's hard. Maybe you understand that pretty easily. Okay? So that concludes this video where we figured out the PI for an amino acid with no ionizable R group. The next one, as a preview, is, this is histidine. Histidine is tricky. Why is histidine tricky? Because at pH 7, look what histidine is doing. There is no charge. I thought these were supposed to be the basic amino acids. I thought they were all supposed to be positive. Well, the thing is, at pH 7, it's not acidic enough to protonate yet the nitrogens. The pKa is, I think, around 6. Or is 6 exactly. So we gotta get it a little more acidic to get it protonated. That's fine. That's totally fine, because look at our trick. Our trick is to start at pH 1. So we will have a protonated side group for histidine. The issue is, and then I'll stop this video, the issue is, at pH 1, do I protonate this nitrogen or do I protonate this nitrogen? Once we get that answer, we're off to the races. We could now start doing our trend where we start increasing the pH as we pass over or cross over each of the 3 pKa's in the next video for histidine. We're going to cross over these 3 pKa's and figure out which two to average. Yeah, let me stop here, okay? And then on the next video, we'll do this page about histidine and figure out, there it is, what the PI of histidine is using a shortcut. This is pretty exciting because, well, if you don't have to, you don't want to have to draw every single structure as you cross over the pKa's. I can't stop talking. Let me stop this video.